Hello everyone, welcome to the webinar on Unveiling Molecules, a computational material science perspective. Now I'm going to briefly discuss the key aspects of material science. As the talk is aimed for the people, those who are in their early research career, I elucidate some parts and especially skip the mathematical equations in the presentation. So this is aimed to provide the flavor of the subject rather than to discuss the things in detail. I request the interested people to follow the given references to learn the things in depth. I have divided the talk into four major sections. In the introduction part, I will give short introduction on material science and materials engineering. Classical mechanics and quantum mechanics are the two major theories used to simulate material properties. I will discuss only some important aspects in both the sections. Recent years, artificial intelligence and machine learning gains much attention and they are found to be very useful in material science regime too. This area is in budding stage and I hope it has enormous potential. So those things will be discussed in the final section. Let's start with the introduction part. We know how important is science and technology in our lives, but most of us don't bother about the key ingredient in science and technology, which is nothing but materials. Just take any material. For example, look into the tire of your vehicle. You know it is made up of rubber, but can we simply use rubber to fabricate the tire? No. It requires processing and validation before incorporated into any vehicle. Likewise, whether a modern computer processor or a new smartphone, we need potential materials that should be tick lot of requirements. So a systematic approach like planning the requirement, design a hypothesis, develop the hypothesis into a product and verify its potentiality is a major arena and we call the entire regime as material science. You may aware that the solid state matter exhibit different physical phenomena in different sizes. Even though we are studying a single atom or a molecule, depending upon its dimension, different subjects or theories were used to describe them. For example, we know steel pipes are made up of iron and some amount of carbon. At electronic level, the properties can be studied using basic physics principles. When we move to atomic scale, chemical principles are more suitable to discuss its structure and properties. At microscopic level, we need to combine both physical and chemical aspects and this region is often denoted as material science. From there, continuum of materials can be studied which falls under the engineering division. So considering material science, we use both physical and chemical concepts to design and tailor a material. Once such a prototype is found successful, it will be moved to engineering division for commercialization. Usually, any subject have some basic objectives to define the subject itself. In the case of material science, it can be designated as material science tetrahedron or in modern terms, material science triangle. The objectives are almost same for both the cases. In tetrahedron, structure is crucial for any material. Once the structure is known, its properties will be studied and processing strategies will be developed. Then, based on this, two performance of the systems will be estimated. But this is no longer holds good due to the fact polymers and composites are play dominant role in potential applications, yet we unaware of their structure or composition. So in modern terms, material science is more about understanding the individual concepts. From there, functional systems will be developed and optimized. For this, both the theory and experimental procedures can be used. But at the end, either performance or optimized data decides the fate of the particular material. So let me to discuss this a bit elaborate. Initially, we should have a hypothesis. For example, if take our previous example of rubber tire, we can expect the following properties. It should have slippery resistance, should have elasticity, and should be durable in terms of mechanical and heat resistance. We may first try the natural rubber as it is to study its competence. Once if it failed our hypothesis, we have to look the ways to improve its properties, like adding fillers or plasticizers. Then there arises a question, what is the optimum amount of mixture? It could be like 70% of rubber and 20% of carbon and 10% of plasticizer, or 60% of rubber, 30% of plasticizer and 10% of carbon. There are n number of possibilities. This is the point where optimization comes. We can try different possibilities, and depending upon the results, we may choose the potential one. For this purpose, we can use either mathematical models or real physical models. While using a model, a definite set of experiments or simulations will be designed. If it is an experiment, instead of manufacture a tire to test its potentiality, we may design a rubber sheet of some centimeter thickness, and it can be subjected to tests like scratching on a rough or a hot surface. Similarly, same environment can be simulated with a computer, and the final output can be collected. Using this data, we can estimate our hypothesis, and if the values are satisfactory, now we may go for manufacturing of a real tire. Remember, still there needs optimization. For example, we have studied only the microscopic properties of the hardened rubber, but still there exist problems like vehicles efficiency variation with a different composition of tire. But those issues are for engineers. We can safely skip those issues now. This shot shows the different phases in terms of materials engineering. In the first phase, as I told in the previous slide, we should have definite goals from which concepts can be developed. These concepts, after a verification, are further improved into a model, and the model based material design and prototype devices will be subjected to trial, usually an physical experiment or a computational simulation. Based on this knowledge, things will be scaled up and subjected to a process optimization. Based on the results, product will be subjected to qualification analysis from there to the final product. For studying materials, both experiments and theoretical models can be used. In the case of theoretical models, they can be broadly classified into three types: classical, quantum, and other statistical methods based on data-driven approaches like machine learning or deep learning. In the following sections, we will see some important aspects of each model. Let's start with the classical models. Classical model is nothing but solving Newton's equation of motion. Often this is termed as classical dynamics, and in the molecular regime it is known as molecular dynamics. Using this model, movement of atoms and molecules will be studied. The principle is like the atoms or molecules are allowed to interact for certain period of time, and we study the dynamics as evolution of system with respect to time. For example, if you see the picture on right side, it is a virus in a fluid environment. So we can study how the virus reacts with the environment as the time evolves. It may form new bonds to the fluid, or the fluid may affect its surface so that it may start to disintegrate. Likewise, any kind of macromolecular interaction can be simulated using molecular dynamics principles. Since it is based on Newtonian mechanics, forces between the particles play a dominant role, and usually the system properties are calculated using interatomic potentials or molecular potentials. It is hard to solve such a systems analytically, so usually specially designed numerical methods are used to solve the system properties. Let's see a bit of history about molecular dynamics. By this time, you may understand that it has deep roots that extend till 15th century. Even though Newton developed the model for celestial objects, he inspired entire scientific community for the next 400 years. Based on Newtonian mechanics, D'Alembert in 18th century developed a method to calculate trajectories of objects, which was rediscovered by Verlet in 1960s to use in molecular dynamics. One important achievement in the development of Monte Carlo method, which actually developed to address Buffon's needle problem. The problem is simple. Let us assume a floor which is made up of thin strips of wood. In case if a needle falls on such a floor, what is the probability of falling between two strips for a needle? The solution is not easy as like the problem. It took another 100 years to solve that issue. In 1902, modern analog computers were developed, and by 1941, scientists used these devices to perform the integration of classical systems. With the introduction of digital computers, the field starts to grow fastly, and the evolution of many body problem as done by Fermi in 1953 using a Maniac 1 model computer. In 1957, Alder and Wainwright solved the elastic collisions between hot spheres using a IBM 704 machine. Even with lighter imagination, one could extend these works to atoms and molecules. And finally, one notable person in this field is a Professor Rahman, who is from Hyderabad, known as the father of molecular dynamics, as he developed some key principles which are still used in molecular dynamics regime. In 64, he studied the liquid argon properties using a Lennard-Jones potential, which is widely opened many doors of molecular dynamics. So, where are these ideas are actually used? As I mentioned earlier, molecular dynamics is for macro systems. So, apart from macroscopic material science problems, MD is widely utilized by biochemists and biophysicists. Since there will be a lot of noise in proton X-ray spectrum or NMR spectrum, molecular dynamics can be used to clean this data and refine the structure of proteins or other biological molecules. In physics, or more precisely in material deposition, the growth dynamics can be simulated using MD principles. In the case of chemistry or in biophysics, MD is widely used in drug design and delivery simulation. Ligand docking is one of the major applications in MD as it indicates potential binding sites in macromolecules. MD can also be used for the prediction of protein structure using random coil assumption in polypeptides. These are some potential limitation of molecular dynamics method. Due to the limitations of their force field, often entropy contribution and intermolecular hydrogen bonds are neglected. So it is hard to predict stability or microscopic properties using MD. Also, usage of macroscopic dielectric constant at short interatomic distance is questionable. One major flaw is MD described van der Waals interaction as Lennard-Jones potential, which literally limits its usage to the soft systems. Before finishing this section, let's see an research publication of molecular dynamics which we published. In this work, we have developed two metal organic systems for photodynamic therapy of cancer cells. From experimental analysis, we found cobalt shows better anti-cancer activity than that of copper-based system. We have used a ligand docking for which we have used a protein called ALK receptor extracted from lung cancer cells. We have found that cobalt system have more binding site to ALK receptor than that of the copper system. So sometimes simulations can be used to tool for better understanding like a problem like this. Let's move on to the quantum models. Quantum model is all about solving Schrödinger equation. I hope you may all aware of the basic principles of quantum mechanics and the significance of Schrödinger's equation. Some of you may even solved one-body hydrogen atom problem in your post-graduation. So the problem with Schrödinger equation is when we consider simple many-body system with more than one atom, it is complex to solve the equations analytically. Historically, many attempts were made to solve the equation for more and more complex system. Here I listed some of the notable advancements. In 1931, pi-electron theory was developed, followed by in 50, linear combination of atomic orbitals, molecular orbitals and self-consistent fields were developed. In 50s, first ab initio calculations were developed. In the next 20 years, fully functional computer packages like Gaussian or Atmolware came to the market. The quantum models can be broadly classified into three categories: ab initio, semi-empirical and density functional. All these methods attempt to solve Schrödinger equation and at different computational costs. Ab initio is most accurate, but it is the most resource-hungry method. Semi-empirical methods are lighter, but at times results could also be too lighter. DFT oscillates between these two. Let's see each method very briefly in the following slides. Ab initio is a Latin word which means from the beginning, and as its name suggests, these methods use very less approximation and apply to the entire system. Solving Schrodinger's equation will yield two parameters. One is molecular energy and another one is wave function. Molecular energy has many chemical significance. For example, more the molecular energy, we could expect an less stable system. Using wave functions, we could estimate the electron distribution in the molecule at a particular instance. These distributions can be interpreted as the properties of a molecule. Since these methods to, have to be solved multiple components, often they are very slow and sophisticated computational facilities are required to perform them. In the case of semi-empirical method also, as like ab initio methods, we solve the entire system. But here, the semi-empirical program will be preloaded with integral library, and whenever a calculation starts, it will substitute the known values, thus improve the efficiency by multifold. For example, we all know benzene molecule. It is well studied and well explored system. Many theoretical and experimental data are available for that system. In case if we wish to study the anthracene, which is nothing but three fused benzene rings, the semi-empirical program will substitute the default bond angle, bond length like parameters of the benzene to the anthracene, then it will solve the remaining integrals. Thus, these methods are much faster than ab initio. But this comes with a cost because anthracene is not benzene. So, parameterization often reduces accuracy. Due to this trade-off nature, every semi-empirical model have to be validated either with experimental or with other higher level theoretical studies. Once these models are optimized, satisfactory results can be obtained. Density functional theory utilizes a different approach to solve the Schrodinger equation. It does not solve the wave function, rather it derives the electron distribution by considering it as a functional. A functional is a mathematical entity which simply means function of function. Here electron density is a functional which is a function of space and time. Often DFT procedures are faster than ab initio and slower than semi-empirical methods. So this can be considered as an intermediate choice. But the results accuracy are many folds better than semi-empirical methods, and most of the time the error percentage with respect to ab initio is negligible. Due to this fact, nowadays DFT is widely used method in material science over ab initio or semi-empirical programs. Since every field in this section is very broad and has many techniques like CCSD, MP, Hartree-Fock, B3LOP functionals or PM6, etc. I don't want to complicate the things by discussing with much details. So you could refer the attached reference for more elaborate discussion. Before winding up this session, let's see an example. The table shows the polarizability and second hyperpolarizability, which is responsible for third harmonic generation, is given. The first three rows represents ab initio methods, and fourth one is DFT, and fifth and sixth belongs to the semi-empirical methods. Final row shows the actual experimental value. In the polarizability, you can see DFT produce good results which are better than ab initio methods. Interestingly, semi-empirical methods are also produce some satisfactory results. This is due to the reason DFT and semi-empirical methods have been tuned over time. But in the case of hyperpolarizability calculations, almost all the methods underestimated the gamma value. This indicates that still we require new methods for solving the systems with complicated physical phenomena. Let's move on to the data science part. With advancement of technology, we have more and more better devices to collect lot of data and have more and more memory to save and process that data. Studies identifying pattern recognition from data become an important scientific regime. But it is hard for humans to identify pattern from such a large data set. So machines were trained to learn and identify pattern from a specific data set, which we call as machine learning, and in popular terms it is called as artificial intelligence. What machine learning does is nothing but standard statistical procedures like classification and regression, but on a large scale, and it learns from the data. So when a new system is introduced, it can estimate its potentiality. Nowadays, it's been utilized in every scientific domain due to their reliable and repeatable decisions. This image simply describes the machine learning process in material science. Data is the crucial part in machine learning. So, collection, normalization, and pre-processing is essential to obtain good results. The data will be splitted into two parts, and major part is used to construct a training set. An algorithm is trained with this data to recognize specific patterns. Then the algorithm will be tested against the remaining data, and its capability for prediction will be estimated. Once this part has been done, the algorithm can be used to predict the actual properties. Let me to explain this a bit more. Let us consider a chemical system like benzimidazole. Many derivatives can be obtained from this parent ligand. Say for example, we have 10 known data for this system. This data is splitted into 8 plus 2 like things. 8 values are utilized for training the machine learning algorithm, and 2 for evaluate the trained algorithm. If the program predicted the values of this data satisfactorily, it can be used to analyze the other derivatives based on benzimidazole. Thus, with minimal computational power, sophisticated results can be obtained. But machine learning is an evolving field. As I mentioned, there were two major areas, classification and regression, are currently utilized for different material science related problems. Understanding the importance of machine learning, many journals published a special issues on this topic, of which one interesting piece of editorial published in Chemistry of Materials in 2019. It lists the top 5 major changes expected within machine learning as well as in material science, entire material science community due to the introduction of machine learning concepts. First is due to less computation power and the availability of many machine learning algorithms in public domain, it is easy to construct and obtain some data from a model. Even in this budding period, already many such reports are available. So we should find a way to validate these results, else it will remain as good as a junk data. Then now we are using standard machine learning procedures which is applicable to each and every field of materials prediction. We need to develop new algorithms that should be specifically dealing materials issue. As data is the crucial requirement for any machine learning algorithm, we should find new ways to acquire data. Conventional programs like DFT can be used to generate required data. On the other hand, by developing natural language processing capabilities, experimental data published can be retrieved and can be processed. Also, machine learning will not applicable to predict the material properties, but due to its versatility, it can be used to assist the post processing and data interpretations. So, literally, it will improve the capability to handle data. Finally, the default physics class has to be embedded into machine learning algorithm. Recently, Google engineers incorporated Newtonian principles in robotic algorithm and makes it to capable of finding the ball trajectories accurately. Likewise, physical laws should be implemented at many levels. Finally, a simple example of a descriptor evolution using machine learning has been discussed. We have theoretically estimated the first and second hyperpolarizabilities of some benzimidazole metal complexes with and without chloride substituents. It is hard to extract the trend from this random data. So we have used a machine learning principle and the which is called a principal component analysis to evaluate the entire group. It is found that chloride substituted molecules show better results, and especially the systems based on first three metals have shown dominant features. Such an understanding can be used when we choose candidates for experimental evaluation or even for the fabrication of prototypes. So at the end of the day, let me to briefly summarize the things. Material science is an ever-growing regime, and still we are in need of potential materials and have to find the possible way to process them. It is not possible to experimentally synthesize each and every system and verify them. Rather, computational methods provide an inexpensive ways to design and tailor novel materials. So the rule of thumb is classical models are for macro systems, Quantum models are for microsystems. Combination of these two by data-driven approaches like machine learning may be used to identify novel phenomena in future. These are some selected reads for those who wish to learn the field in depth. I personally suggest the first two texts as they provide basics in a very nice way. June Lee's Computational Material Science is also a very nice text and explains every method with worked examples. Finally, like any modern scientific work, the talk is directly and indirectly contributed by many friends and colleagues, of whom I wish to particularly thank two who directly contributed this presentation. Dr. Suresh for the encouragement and analysis and key suggestions, and Dr. Jyoti Murugan for presentation delivery related suggestions. Last but not least, thank you all for your presentation and spending your time here. Thank you.